Hello. Hi, is it working? Okay. Hello, everyone, and thank you for joining me here for this talk. And for those of you who doesn't know me, my name is Vlad, and I'm the author and the maintainer of the Finch library, a Scala combinator library for building HTTP services. And no surprise here, this is what we're going to be talking about right now. But instead of going into some API details, examples, and case studies, which is kind of boring, I think, mostly because there's not much to talk about. The entire API surface for Finch is just one abstraction, basically one type, and the collection of methods defined on top of that. So there is not much to talk about as far as the example goes. But instead, I want us to focus on something different, and I hope something slightly more entertaining, especially for the Finch users. But it's not absolutely necessary to be familiar with the library to enjoy this talk, I hope. And everyone is welcome here. Aka HTTP users, Play users, Spray users, it doesn't matter. I hope you'll find something useful in what we're going to be covering today. And so we are going to talk about performance of the HTTP libraries, and specifically about Finch performance. And before that, we'll try to real quick focus on this main abstraction Finch defines. It's called HTTP endpoint, and see how it actually makes sense to define these kind of abstractions for HTTP applications and how expressive and composable it might be. So let's get this ball rolling, I guess. So the title of the talk says that we should put some types on our HTTP endpoints. And the question is, why should we care about that? Why should we be doing that? Because, TCP doesn't care about types. It's all bytes there. And the bad news is HTTP doesn't care about types. The only type it cares about is a string, which is basically an array of bytes. So it looks like we're kind of in a bad company here, because we're trying to develop web apps like HTTP applications, and everything in our stack, networking stack, doesn't care about our fancy types. And it's kind of a bummer, because types are nice, they're great. They allow us to fight the complexity of the domain with basically clearly defined abstractions and match-and-checked composition rules. And the good news, though, that our compiler cares about types. Scala cares about types, and we should all care about types as well. And I think it's pretty obvious at that point. So, and the question is, it looks like what we want to do is some kind of typed HTTP. So, and the main idea is that, isn't this already typed? I mean, HTTP, most of the libraries expose you some kind of HTTP requests and HTTP response types that you have to deal with this. Finagle do that, for example. And that's perfectly fine. That's all right. That's, those kind of types allows you to be really precise what you want to do in your application. But the problem is they don't actually mean a lot in our application domain. They're rather like a transport concerns we shouldn't actually care about. And things like HTTP entry, HTTP header, like more fine-grained structures only make it worse by polluting our code base with these transport level concerns and abstractions. And so maybe we should be doing just strings instead, just model everything as strings in HTTP. And it's perfectly fine, but I think we can do something better, something more high level than strings, something more usable. And what type is better than string? And basically any type is better than string. And well, A is kind of like a type param. And why don't we use this abstract type, this arbitrary type A, to model HTTP? And in this case, A could be anything. It could be HTTP request, it could be HTTP response, it could be even string if you will. And it's perfectly fine. This is exactly what we want to do. But the question is, where should we put this type? Should we put that on request, maybe response, like request of A, maybe response of A, or something like that? And if you think about this more and remember that, like for example in Finagle, there's this model, your server as a function. So your server is a function from request to response. And if you take that function and leave that into some kind of context called endpoint, you will basically promote that function into some high-level abstraction well, maybe a monad, maybe an applicative, depending on how this context is implemented. So if you have this, you can model HTTP, basically this request to response relationship, which is mapping the endpoint from endpoint of request into endpoint of response. And you're done. Basically, the job is done. And yeah, and this is what Finch is about. It gives you this HTTP endpoint abstraction of arbitrary type A, and it defines a bunch of combinators for that. So you can use it to build more complex things out of the simple things. And it's been around quite a long time and got some reasonable level of adoption already. And it's surprisingly lightweight and fast, given how far it goes into the purely functional land and how many levels of indirection it involves on top of its foundation. And as far as the foundation goes, it's all these libraries Scala community seem to like. Obviously, Finch is using Circe for JSON because Circe is awesome. And it's really fast and lightweight. If you haven't tried it yet, you should totally do that. It uses shapeless for compile time machinery and genetic programming, and for Circe as a genetic derivation tool. It uses cats for basically support for type classes, like well-known type classes. And as far as the transport goes, it runs HTTP server on the Finagle library, which is, if you haven't heard about that, an RPC stack for the JVM used and developed at Twitter. And it's really great thing. It's been around quite a while, since 2010, when nothing else was around. It's actually really, really old and battle-proven working code that is easy to operate and scale, and it comes with quite rich infrastructure in terms of support to different protocols. You can think of Redis, HTTP 1.1, HTTP 2 coming in a couple of months, Thriftmax, things like that. You can do all sorts of things with Finagle, and in addition to that, you'll have some notion of observability extensions like matrix and distributed tracing. You have all of those, and the nice thing about that is when you start using Finch, you don't have to absolutely necessarily use all of those. You can start by just running your Finch endpoints within the Finagle HTTP server, and then adopt all of those small pieces from Finagle, like different clients, protocol, metrics, whatever. As far as your organization grows, as far as you need that, you can do all of this incrementally and try to basically use everything Finagle has to offer. And this is really nice. And with all that hate to Twitter features, which I think perfectly fine, I think Finagle is a huge selling point for Finch because this is really, really nice and rich infrastructure for that kind of thing. Right, and as far as the shapeless goes, just mention real quick, if you're scared about that, it's not a big problem because if you want to use Finch, you don't have to be an expert in shapeless. Everything is structured in a way that you can avoid seeing those types, like shapeless types in your Finch applications, unless you absolutely want to do that. And the nice thing about that, you can always drop down to shapeless types and empower some genetic programming and really nice compile time features. So, but again, you don't have to be an expert in that. You don't have to use it from where you start, from day one. You don't do that. Right, so let's talk real quick about endpoints itself. We already talked that it's some kind of a context we want to implement for HTTP. So we want to map things, basically go from HTTP request to HTTP response, so there is functor. And what else could be nice to do is, let's say we have two endpoints and we want to compose them in terms of product or co-product. So we've got an applicative, we can do that, which is really nice. And if you think about the internal details, basically an endpoint embeds some kind of state T monad transformer. So it takes an input, some abstract immutable state, and it produces you two things back. The first one is a reminder of the input, and the second one is actual output. So, and you don't have to reason about that thing at all. It's just like necessary for the rest of the talk. But when you use Finch apps, when you run Finch endpoints, you don't have to understand the last part here. The only relevant for you as a user is those two things. You can map endpoints, go from underlying type A to underlying type B, and you can compose two endpoints in terms of two different things, as product and co-product. So if you compose them as product, you'll get two things in output. And you compose them as product, you'll get either A or B. It's that simple. Right, so finally some example. And on the left side, this is the Finagle HTTP service that takes a post request and reads the JSON body as a case class payload, and then writes that JSON body back to the client. So it's sort of like an echo service for the JSON object. And so there are lots of going on here, and the most relevant parts are highlighted yellow here. So those are three things we have to keep in mind and care about. It's just the post request, this is the first thing, and then we read the JSON body as payload, and then we serve that back. Everything else is just some kind of noise, some kind of machinery boilerplate we have to maintain for the service. And there's nothing wrong with that. It's just how the things works here. And so how is the same thing is implemented in Finch looks like? And it basically this little guy here. And it's all highlighted yellow because everything is important here. Every single word here is basically express some context about what's going on. So basically we got post request, we got JSON body, and we have a case class payload. And this is the self-contained endpoint you can run just now, and it will work perfectly fine. And this is, in fact, exactly what we're going to do right now. So I have this REPL session right here, and it's just basic Finch from master, I guess. There's nothing too crazy going on. We just import Finch and Circe support the genetic derivation for Circe because we don't want to write encoders and decoders for JSON types yet. And yeah, let's say we have this case class payload that has two things in it, basically an integer and a string. Sorry. Oh, it's a case class. Right, and so we just go ahead and define the same endpoint we had. And basically, we've got post, we've got JSON body of the case class payload. Payload, that's right. It's not right. It's a payload. What? Did I? Oh, yeah. Sorry for that. What? What's going on? Is it right? Of course. Okay, perfect. So we've got an endpoint of payload, and if you think about that, this is the thing that accepts a request and gives you back a payload within the HTTP body. So this is all we have to understand about that. And now we're going to go ahead and serve it this in Finagle. The way you do that, you say just serve, then you need to define some port, and then you say this is going to be servers as application JSON. So you have to specify the content type for that thing. And this is actually a type. So content type is a type in Finch, which is really nice because it affects the way you derive encoders and decoders for the supported library, like JSON or XML, whatever you're going to use here. So yeah, so we run the server, and it says everything is perfect and fine. And now we can query that. So I'll use HTTP, I think that's how you spell it. You just say what port you're going to use, and sorry for that. What else? So we have this payload with two things. There is integer and string, and we say integer is going to be 10, and the string is going to be 4, right? And the HTTP converts that into the post request. So you will get that the response of that payload case class, the same one we just sent in. And that's it. That's the whole thing. The nice thing about that, let's shut down the server for now. The nice thing about that is that you can take that endpoint and basically map it if you want to change something. If you want to introduce like business logic or how you call it, you can map this thing just like that. You say, this is the payload. It was a payload at some point, and we can build a new one, right? We can say payload. This one is going to have the same integer. We can multiply that by 10, and this is going to have the same string. Let's say multiply by 10. why I'm doing this again? Okay, so we've got the same endpoint, kind of the same, but it has some business logic in it as a map function. And yeah, we do the same thing. We serve it, again, the same way using the Finagle server, and we query that, again, using the same thing. And we've got a response back that has an integer multiplied by 10, and it has 10 foods in it, right? So that's basically about it. You just map it as like option or list. You just use map to transform your stuff. And just real quick, you don't absolutely necessarily have to use map. There is some kind of ScalaMatsuri-like syntax for that, empowering the endpoints. So instead of doing map here, if you don't like it by some reason, you can do slightly different thing. You can say, this is the apply method, and we apply that to function. So we have this payload, and then we just do the same, but wrap it within the context, OK, which is basically HTTP 200. And yeah, that's basically it. You just close your stuff, and you do the same thing. You serve it again, and we can check that it works. Sorry. And it does. So you have this kind of like nice syntax if you prefer, but you can absolutely use map, or you can compose things using the API Endpoint provides. You don't absolutely necessarily have to use that. So this is like all you have to know about endpoints to start using them. You don't actually do some crazy stuff. You don't bootstrap anything. All you have to know is you build an endpoint, and then you do this HTTP server thing, and everything just works. Okay, so this is nice. The question is, it looks really compact and expressive, right? So it must be really, really slow. It must cost you a lot. And in fact, it doesn't. So this is the most recent run of the Tech and Power benchmark. If you haven't heard about that, this is the open source benchmark they use to compare different HTTP libraries, HTTP frameworks, not even Scala ones, like every single language. And the nice thing about that is when you define a new benchmark for your library, you can specify what foundation it is using. For example, for Finagle, it's going to be Netty, and for Finch, it's going to be Finagle. So when you do that, you will get this nice comparison chart, and you can see how much overhead your library introduces on top of the foundation it runs on. And for Finch, you can see that it basically runs on 90% of Finagle throughput. So it only gives you like 10% of the overhead over the raw Finagle service. And the Finagle service is actually looking kind of like that for that benchmark. And Finch exactly looking kind of like that. So it's really impressive, by the way. So, and well, on one hand, it is impressive because 10% is not a lot. But on the other hand, it's sort of like a lot, right? Because why it's 10%? Why it's not 0? It should be 0, maybe. So bear with me. Let's see if we can understand and explain why we have this 10%. So in the first thing we're going to talk about, why it's only 10, why it's so small, why the endpoint abstraction is so lightweight that it only gives you 10% overhead. And yeah, the main idea is that a lot of things happen at compile time. And it's actually quite cheap at runtime, because when you trade off your compile time for basically usually cheaper and safer runtime. And if you think about that, you can, for example, Circe, like Finch is using Circe for JSON decoding. Like instead of using runtime reflection and inspecting every single object at runtime in order to figure out how to properly encode or decode that from JSON, Circe has all its decoders and encoders materialized at compile time. So when your program runs, you already have them in place. You don't have to build them again. You can just reuse them every time you've got an object. And this is really cheap, actually. And Circe is fast, really fast because of that. One of the reasons because of that. Yeah, and the same thing happens for endpoints, because when you compose endpoints, every kind of check, every logic happens at compile time, and then you just run it. You already have it in place. You don't have to do anything else. You don't have to check anything else at runtime. It's pretty cheap. Yeah, and as far as the foundation goes, there are several things Finch is trying to improve in terms of using the most efficient way of decoding or encoding the payload at this particular time, depending on the supported JSON library, enabled JSON library at this point, or a Finagle setup. And because it owns this decoding and encoding layer, so you don't worry about that. It's actually quite possible to do nice things there at that point. And this is what we're going to be talking right now in the next couple of slides. And yeah, the last thing, I guess, is Endpoint itself as an abstraction. It's not completely broken performance-wise. It's actually quite nice and lightweight, turns out, because it's been around quite a while, and lots of people adopted that, and nobody complains about performance. So I guess it works fine. Yeah, sure.
What exactly does the previous benchmark measure? Does it?
It's a throughput of the service, HTTP service. So yeah, good question. So this is the benchmark, the Tech and Power benchmark. It's a really simple thing. It gets requests like hello or something like that, and it gives you back a JSON payload saying hello world. And there are some rules you have to obey, like you have to allocate a new payload every time on every request, so you cannot pre-allocate that and reuse that. And yeah, and if you can see that the first column here is basically a QPS. So for Finagle is going to be, what is that, 330K requests per second, and for Finch is going to be 300K requests per second. So it's not a lot. It's pretty comparable. Right. So now let's talk about why so much, why it's 10%, why it's that a lot. And yeah, I think it's pretty obvious that composition comes with the cost. You have to pay this price in terms of allocations when you compose things. And this is somewhat fundamental because if you think about that in the object-oriented setting, when you want a new behavior, you just take a class, you extend that, you inherit the old behavior, and you can allocate a new thing in one shot, and you will get the job done. In the purely functional setting, in order to get something new, you have to allocate something all that the first time, and then you have to compose that with something that changes the behavior. So you have to allocate at least two things to get the job done. And this is quite a lot of difference here. And yeah, in fact, JVM doesn't frankly like allocations because especially those surviving several collections. So your application actually has to go and copy some garbage around instead of servicing your request. And this is quite painful. And the problem is that idiomatic Scala code allocates a lot. All those idiomatic concepts like immutability and compositions, they're all about allocations. They cost allocations. And don't get me wrong, I'm not against idiomatic Scala. I think it's a perfect tool, especially because it basically allows you to, within a small local scope, to use some mutable state like vars, use mutable arrays, do while loops, everything which is perfectly fast in JVM. You can do all sort of things within a small local scope, and it still can be called idiomatic Scala because you expose a proper API for those kind of things. It's all hidden. Users don't see that. But the things get much worse when you enter the purely functional land, where those arrays and vars aren't welcomed at all. And then this is when your allocation profile changes a lot. That's a big deal. So, and this is somewhat counterintuitive, but it turns out that fast Scala code doesn't actually look like Scala. It looks like something different. And if you want a good example, there's this a JSON parser library called John. It's really fast. Circe uses that. And if you just go check it out, see its source code, it doesn't look like Scala. It's totally mind-blowing, and it's really fast. And yeah. And besides John, there are several libraries that consider it fast, and they actually don't look like Scala. They look like something different. And they all solve different problems, but they all look alike in terms of trying to not allocate a lot of garbage and adopting things like mutable state, like even local, maybe not even local, some arrays, while loops, and things like that. Everything we hated so much, we switched to Scala from Java, right? Yeah, and Jill 10, one of the authors of the C4 garbage collector for the JVM, pauseless garbage collector, summarizes this concept in something really weird. How to make X faster, do less of X. So how to make Scala faster, do less of Scala, right? This is kind of terrible, right? Because we all wanted so much to write this nice immutable concepts, but Turns out we cannot do that because they're slow. And it's not actually true, because in most of the applications, you don't have to worry about them. What I'm trying to say is that there are several cases, like foundation libraries, like Circe, like Finch, everything you're going to run on every request, everything that is placed on the hot path. So for those things, it kind of makes sense to trade off those fancy concepts for performance and adopt some ugly things, right? So you all as users can enjoy fancy Scala and still maintain reasonable performance with that. Right, so let's see how Finch adopts those two things. Basically, how to make Scala faster, do less of Scala, and how to make composition faster. Let's just maybe compose less, right? And remember we talked about this state T-monad transformer within the endpoint. So if you think about that, you have an endpoint, basically a function. So it takes an input and produces you two things, a reminder of the input and then the output itself. So in one way to model that is to wrap the whole thing into a tuple and run an option. So we need an option to model this, whether or not endpoint was matched on a given input. So the idiomatic Scala way of doing that is have this option wrapped in a tuple, and it's perfectly fine. This is exactly what you're supposed to be doing in Scala. It's perfectly idiomatic, and it's really nice because you don't have to maintain that. You get all those nice things like maps, flat map, collect, all the support from the standard library, and composability. But the other way to do that is to hand roll your own thing, which is basically an ADT with two cases. One of them is skipped, one of them is matched. And match is basically a flattened version of the option and the tuple. So we get the tuple and basically flatten that into the option. And if why we do that? Because, for example, when you try to allocate the successful case, when the endpoint is matched and you need to return some result, when you do that and use option, you have to allocate a tuple, and then you allocate an option, so two allocations. And for the ADT case, you just do that in one shot, and you have one allocation in total. And if you think about that, the later solution is really less powerful. It's kind of ugly. It doesn't have map. It doesn't have flat map. So if you use that, you have to use pattern matching to get the job done, which is pretty ugly, maybe not even idiomatic Scala, totally not purely functional Scala. So, and with option, you can do map, you can do flat map, all nice things. And those things cost allocations, again, because you have to allocate the closure to pass into the map function or flat map function. And with using pattern matching, it's really bare bones. All you do is just pattern match and then do stuff. It costs you nothing. Pattern matching is basically free in Scala. And you might think it's not a big difference, but in fact it is. Here's the benchmark results from the JMH benchmark. And this is the running time mode, so less is better. And this is for one particular benchmark, basically endpoint.map. And we have two different cases. We have this type LST option, and we have this ADT case. And you can see that we basically saved around 56 bytes per one call and something in terms of nanoseconds, which is basically not much. But if you remember that Tech Empower benchmark when Finch is doing like 300,000 QPS queries per second, that sums up to a lot of allocations. And we can see if we save them, the JVM will thank us later with basically rare GC pauses. And that's a big deal for such a small change. There is some links, and I posted, sorry, I really forgot to tell that, but I tweeted the link to this slide deck under the ScalaMatsuri hashtag. So if you want to go ahead and check this out, you will have the same slide deck, and you can click all those links to go and follow the basically how the whole thing works here. Yeah, so what did we learn so far about this particular case, compose less, is basically, yeah, there are lots of reasons to introduce a new type into your domain, into your application, but by far my favorites are less powerful abstraction and better performance. And turns out those two things usually came in a package. So you trade off for one of them, and you get the other for free. And the same thing happens for basically an API. When you design something new, some new type, a new abstraction, you can try to think about it where you want to use that abstraction. And if it's placed on a hot code path, you'll probably want to try to make it as simple as possible and try to restrict its API, for example, to not engage composition because composition costs allocations. And you can make it really stupid and ugly, and it will be really fast. Yeah, and of course, bytes matter. You always have to remember that, but check JMH. See how exactly you can save. There's this nice flag you can pass into JMH library, which is basically prof.gc. It will print you the allocation profile you can check out for your methods. Yeah, always remember that if you save several bytes on one function call, it will sum up into a lot depending on how many times you call this function in your application. And basically you do that on every request for the foundation libraries like Finch or Circe, things like that. Right, so let's talk about second example real quick. So the first one was focused on Scala itself, how to make composition faster. And the second is more like generic, basically idea, like how to make codecs faster. Because in HTTP libraries, we have lots of different codecs. We have a JSON codecs, we might have XML codecs or something like that. And if we default to the JSON case, which is really simple, we do a lot of JSON decoding and encoding. And the question is, can we make those things faster? And yeah, let's figure this out. So here's what happens on the HTTP land for the inbound requests. When you get the HTTP request, you've got some bytes off the wire. And what you want to do, you want to decode them as a JSON object, obviously. So you do that, the way you do that, you convert those bytes into a string first, because most of the JSON libraries parse strings, and it's pretty dumb. Though, anyways, you do that, and then you actually get some JSON object out of that when you can send that string into the JSON library to parse that. And if you think about that, this intermediate step, going from byte array, is kind of weird because it just transformed the data we already had from one form into another form just to satisfy the API of the JSON library we use. And it might not be a big deal, but the problem is on the JVM, when you try to convert the byte array into the string, you actually have to allocate the same size char array for the byte array. And you know that each character on the JVM is 2 bytes. So it basically means 2x allocations. That's a lot of allocations. And why don't we just, go directly from byte array into the JSON object? Why don't we just keep this intermediate step we just want to throw on the ground because we need it just to satisfy the API? And it turns out that what we want to do is just parse JSON from bytes, right, from byte array or something like that. And most of the modern JSON libraries can do that for you. And the good news is John can do that for you. So both Circe and Argonaut, they can do that. They support this API. People just don't use it by some reason. And the only difference is, the only one thing you have to keep in mind, that your byte array for your JSON string should be UTF-8 encoded. This is the only restriction you have to follow. And if you use that, that's a nice thing, and that's implemented in Finch 0.11. Out of the box, you don't have to enable that. It's always there. And yeah, as far as the implementation goes, it's really simple. So you have this Circe decoder, and you check the input char set. And if it's UTF-8, you can decode byte array. And if it's not, you default to the string-based case, which is really slow. And yeah, let's check some benchmarks again. Running time benchmark, less is better. 2 cases, we have parsing string, we have parsing byte arrays, and you can see that we basically cut allocations and running time in half by just not doing some useless work. There's nothing magical about that. There's no smart-ass algorithms here, compiler tricks. We're just not doing some useless work. We're just doing the work that is important in our application. And yeah, and because Finch owns that decoding layer, basically, this is why we can do that. Technically, every user should be doing exactly the same thing in the HTTP library they are using. So it just in Finch, you give that, you get that for free. That's the difference, I guess. So the same kind of thing happens on the outbound path. So let's say you have this Scala case class you want to send back to the user. and you want to encode that as JSON. So the way you do that, first of all, you print that case class into the JSON string using the JSON library, obviously, and then you convert that string into the byte array so you can write into the wire. And again, you see where it's going. The middle representation of the data you have. It's not absolutely necessary, and it's quite expensive because going from string to byte array also means allocations and copy stuff around. So why don't we just print directly into byte array? It's super obvious. And yeah, in fact, we can do that. Not every single JSON library supports that. This is a bummer, but Jackson can do that for you, and Circe starting from 0.7 supports printing onto byte arrays directly rather than strings. If the target char set is UTF-8. And yeah, starting from Finch 0.12, you will get that for free. If you use standard UTF-8 char set, you'll get printing into bytes. And again, the implementation is very simple. You've got this Circe encoder, you check the target char set, and you default to byte array rather than string. If you can do that, it's going to be really fast. So here's the benchmark result. Again, 2 cases, less is better. And yeah, and basically we see that we saved about 30% in terms of allocations and running time, which is really nice. So, so what you want to do here is if you use Finch, always UTF-8, and you'll get everything running as fast as possible. So here's what we've learned so far. Going from string into byte array and vice versa isn't that cheap as you might think. It's actually pretty expensive, and most of the time unnecessary. And the problem is it's really hard to tell if it's necessary or not unless you're looking at the whole problem end to end. So I encourage everyone, try to look at how data flows through your application, basically what stages you have, and see if you can simplify something or even eliminate some stages itself. And yeah, so, and everything we just talked about that is available in 0.12. You can try it out. Yeah, so the summary of everything I kind of learned trying to do all this performance work in Finch is that performance-wise, it's really hard to reason about Scala code. And I think you all agree with me with that, because there are so many different moving parts around. It's really hard to tell what's going on unless you use some specialized tools for that, like JMH benchmarking. And I encourage everyone to try it out and check how fast your Scala code runs. And most important, you have to pay attention to the allocation profile, especially for the, for the hot path, for the code you're going to execute on every request. And yeah, try to master a new trick, knowing how to allocate less, doing X. Like every single thing, there is different ways to do that. And basically, you should prefer the one that allocates less, if you can do that. And yeah, do less of X, obviously. Do less work if it's possible, the least possible amount of work to get the job done. And yeah, check out the Finch project on GitHub. And I guess that's all I have. Thank you very much. I think we have like 2 or 3 minutes if you have any questions.
はい、どなたか、ご質問のある方おられますか？
Sure.
Are you using Finch in Twitter production?
No. Good question. Yeah, the question was, are we using Finch at Twitter in production? The answer is no. There are plenty of different HTTP libraries used at Twitter. At that point, there are several of them, and we don't need another one. Yeah, Finch is basically an open source community-driven project. It's not strictly related to Twitter, rather than it uses Finagle as a foundation. So there are plenty of companies using Finch in production, but not Twitter. There is a question, I think.
So I saw a benchmarking graph, and I wonder why Finatra is faster than Finagle.
Finatra, why Finatra is faster than Finagle?
Yeah.
This is a good question. And the answer is Finatra had some basically HTTP specific optimizations that wasn't upstreamed to Finagle yet. At this point, as of today, they all upstreamed and ported to Finagle. So when the Decompower benchmark is going to do the next round, when they run a new version, it should be pretty aligned at that point. Good question. Thank you. All right. Thank you very much. Thank you for coming.
じゃあどうもありがとうございました。Thank you very much. Much.